currently he's a lecture professor here in Barcelona at Universitat de Barcelona. And so thank you very much, Roberto, for accepting giving a mini course here. And so the stage is yours.
Yeah, thank you very much. And it should be me who thanks the scientific committee and especially the local organizers for putting this activity together in these difficult times, and also to being so flexible within like just within a few days to set up the activity so that I can give this course online. I would like to talk about generalized geometry and complex Dirac structures. So in order to talk about generalized geometry, it's always good to remember what we do in geometry, and I will take this opportunity to fix some notation. So I'll start by sharing my whiteboard here. So in geometry, we study some objects which are smooth manifolds. I will denote them by M. So remember, a smooth manifold, I define it as a topological space such that I have some open sets that go to homeomorphically to some open set of Rn in such a way that whenever I have an overlap, so this is going to be smooth. So having all those charts all together compatible, this is what's called an atlas, and this gives a structure of a manifold to a topological space. The thing is that when we want to put geometric structures on such an object, you can do it by changing you could potentially change your chart here. For instance, you could say this goes to Cm, and you could say that the maps between them now, instead of being just smooth, they have to be holomorphic. Okay, so it's very powerful, but at the end it's very complex indeed. So what we geometers do many times is that instead of looking so much at the manifold and at the charts, we work with an object which is the tangent bundle of a manifold. So for that, for every point, we know that we can associate a vector space, and we like vector spaces. We started doing geometry in vector spaces. If you remember, drawing triangles, all we did since we were 4 until we were probably 20 something, it was just vector spaces. So remember, just for me, I mean, you can define it directly as derivations, but I like to think of them just as these curves going from some neighborhood of 0 to your manifold, passing at time 0 through P, and then I put those brackets because there is an equivalence relation, and what I do is just actually I'm saying that two are equivalent if and only if I will have that these derivatives at 0 are the same, and this I do it actually for functions from M to R, and let me just call this, and I will now introduce this notation Fg, and these are what I call C infinity functions, smooth functions, because remember, I put smooth structure on a manifold in order to do calculus analysis on my manifold. So in particular, I can talk about smooth manifold, smooth functions, which are the ones such that when I compose with the chart, okay, I will get a smooth function. So this is just a vector space on a point. So what we will use in this course a lot is putting together all these tangent spaces and actually some similar objects. Okay, so the thing is now to define consider all of them at the same time. So I take all of them at the same time, and this, it's called the tangent bundle. It comes with a projection to M, to your manifold, in such a way that this is just, so if I give you now V is a vector, okay, so V would be the class of one of these curves. This just goes to P. As it stands now, this is just a union of vector spaces, but it turns out that you can give to this a very nice structure. This is actually what's called a vector bundle. Okay, and a vector bundle, what it is a smooth manifold, like one of these. I painted on the left hand side, smooth manifold E with a projection to a base manifold, going just to click PR. Okay, and then if it's vector, is because the pre-image of any point, which I denote by EX, which is just taking this projection, taking the inverse image of an element. I'm going to keep the same notation. I'm going to keep P for the point. For the point, this has a structure of a vector space. And then there is something special about bundles, which is that locally, they are just going to be the product. Even globally, they may not be a product. So I will say that there exist trivializations around each point. I don't want to do this very long. And around each point, my bundle E U is like U times R, and then some RS, okay? And what happens is that in the same way that these charts for a smooth manifold were compatible because the change of chart was smooth, okay? So here, the changes of trivialization are also linear. Okay, we won't be using like all the details of this definition, but the most important thing is to know that we have the projection, that we have this structure of vector space on every what's called fiber of this vector bundle. Okay, so this is just one of them, is perhaps the most important one, is the most basic one, because what's doing is at every point of my manifold, I'm putting on top a vector space. Okay, so and I'm considering this, and I give this the structure of a smooth manifold. Okay, that talks very nicely with the base manifold. Of course, this is keeping the complexity of the manifold M, but it's adding some information, which is, if you want, at every point you are somehow losing information because the vector space doesn't have as much information. But we mathematicians, what we often do is, among all the information we have, we want to find just the information, the minimum information we need in order to be able to say something or to deduce something. This is, for instance, invariants are this type of information. So somehow the tangent bundles should be regarded in the same way. Along with the tangent bundle, where over each point I put this tangent space, I can put the dual of this tangent space, and I can do the same construction. So I would have the cotangent bundle just by taking the duals of these vector spaces I just put, okay, with the same projection. And this will be also a bundle, which is also important to us. The other two examples I'm going to use are the bundle of my vectors. And the thing is, any operation you can do on a vector space, you'll be able to do it on a vector bundle, as long as it is factorial, that it works nicely. So in the same way that I put tangent spaces over each point, I can also put the second exterior power of the tangent spaces. Okay, and of course now no one stops me from taking also kth exterior power of the cotangent ones. And one thing that is very interesting in this case is that because the exterior power of a vector space, if I take it many times, more than the dimension of that vector space, because it's skew-symmetric, it will just become 0, I can actually consider a super bundle, which is the exterior bundle, which is just, and here I'm using another operation. As I said, I can take exterior product of exterior power of a vector space. I can take exterior power of a vector bundle. I can take direct sum of vector spaces. So I can take what's called the Whitney, okay, which is just a direct sum of vector bundles. So this thing here will play a very important role in what we are doing. Okay, I take from 0, which is just a trivial bundle, because the theory of the 0th exterior power is just to be considered the field, up to dimension of m, which is the last one, which is non-zero. Okay, so this actually is exterior bundle, and in here I have a operation. So this is actually an algebra. Okay, the sections are an algebra with this. Okay, so okay, I haven't said what sections are, so this would, let me just say this will be an algebra with the wedge product of forms. Okay, so remember, an algebra is just a vector space. So I know how to sum these things here because they are all vector spaces. I know how to multiply by a scalar. And now I have this operation, the wedge product, that will allow me, if you want, for now pointwise, to give another element in this exterior bundle. Okay, so I was already saying another keyword for us, which is section. So what a section is, let me just explain here in the drawing, is, well, we put on our manifold, at each point, we put some information. So why did we do that? Because at some moments, we will need to say at each point what of that information we are keeping, okay? So if at each point I choose an element, okay, in the space I'm putting there, this is called a section of a bundle. So let me just write it here. So what's a section of a bundle, which I will, as I put it later, sorry, before I said just this manifold with this projection. And here actually I'm saying section of a bundle, it will be, for us, they are vector bundles, but this applies in general for this larger class of fiber bundles. So I'm going to say it's a smooth map. I will always consider smooth objects. So whenever I don't say smooth, and it only makes sense for smooth, so it is smooth. Sometimes I will stress that they are smooth. Okay, so what I want is to choose for every point of my base manifold M something on the fiber. So the way to express that mathematically is like a map, such that when I take the projection of the section, this is just going to be the identity on my manifold. Okay, so this I will denote it. Okay, denote it that S, and I use this symbol gamma of E. Okay, so this capital gamma denotes sections, and it may happen, sometimes you have only local sections, may happen to us. So if you have just U here, like some open set, and you have S that goes from U to, and here I say E, okay, I will just use this symbol restricted to U to say kind of, I'm just taking U with the fibers on U. So this I will denote it by S is a section from U to E, okay? This is very general, and I want to talk about concrete things. So I will now tell you what are the letters I will use for the sections we will see. So this could be considered an example, or could be considered also that I'm introducing the notation. So examples, or and also the notation I'm introducing is that whenever I have sections of the tangent bundle, I will denote it by X and Y usually, okay? So there are maps M to Tm, choosing those vector fields. And these, I will denote them by this symbol, and these are what's called vector, okay? These are my vector fields. When I have sections of the tangent, the cotangent bundle, this I will denote it by omega-1, and these are just one forms. If I have a section of this wedge 2 of Tm, this I will denote it by this thing, and this is just a bivector field. I will just call it bivector. And if I have, say, phi or rho, I will use, I have a section of this very big bundle. This just will be denoted by omega bullet, and this is just a form. Okay. So one thing I can do, one operation that I will use quite a bit in the course is the insertion of a vector field. Okay, and now I'm going to make use of the notation. You see, now I'm saying, okay. So this is an operation which actually is a linear algebraic operation. It belongs to the world of linear algebra. I could have talked about it before. Okay, just for convenience, because I'm going to use it for sections, I put it here. But if you took a look at the notes I sent you, this was defined just at the level of the bundles. So this insertion is just saying, okay, whenever you give me one of these forms, okay, what is one of these forms? So one of these forms is for each point, you are giving me an element in here, okay, like of this super exterior power of T star M. So what I'm going to do, if this, I call it phi, okay? What I'm going to do is to give you another element of those forms, and here I'm going to put -1 to say something that whenever this thing had components of different degrees, say 2, 4, so what I'm going to do is just to do phi of x and just leave the other ones free, okay? So this is the insertion operator of a vector field acting on forms. So that's all I wanted to review about sections. Let me just put here now what I want to say about vector fields. Okay, this is kind of a differential geometry course in 20 minutes, but it's good that we all have the same notation. What's the thing about vectors? If you think about it, at first the definition of vectors starts very well, because you say, okay, there are equivalence classes of curves on your manifold, but then this equivalence is made through this thing of, and now for every smooth function you have, you will compose a smooth function with your curve. You will take the derivative in 0 and you will see if that coincides or doesn't coincide. So this is telling you that actually the person who defined that vector space in terms of this equivalence class of curves, what had in mind actually was that a vector should derive functions, okay? So this is a very important fact. So these vectors on vector fields, okay? I'm going to say here vector fields better. And the way they do it, okay, so it's just, I mean, now we found what they were plotting. So it's not nothing very surprising. Is that you give me a function f, okay, and the vector field is x. So what you do is, okay, what's the value of x of f at a point p? So, well, it was everything ready because you know that xp is just the equivalence class of some curve. So now you just give me a value, you have to give me a number then because you have to give me a function. So you just do this, okay? So, and this doesn't depend on the curve. Why? Because it was all set up, okay? We've been tricked. So this is just, give me a function. For every point, give me a number. So this is giving me another function. And you can check actually that this is a derivation, okay? It satisfies the usual derivation properties. So it can be proved, and for that, of course, you should go to your favorite differential geometry course, that vector fields are equivalent to derivations. And this I'm just saying to introduce an object which is very important for us. We'll see it a lot, which is now we can do the opposite thing. We can say, okay, so instead of giving me the curves, give me a derivation. And if you give me a derivation, because of this correspondence, that will be a vector field. So this is what is done for when I have f, and if I give you first I act, if I have for two vector fields. And now I'm going to use my notation, x, y, which are vector fields. It turns out that f going to, and now I do the following thing. I first derive by y, I first derive by x. This, by the way, is not a derivation. You can check it, it doesn't work well, but then it turns out that if you do this, this is a derivation, okay? Because you cancel out the things that were annoying. So since this is a derivation, we are going to give it a name, okay? It is called the Lie bracket. And denoted by this, okay? So this has actually, this Lie bracket has a kind of dual operation, okay? Because what I'm doing here is, given a vector field, I can derive a function, okay? So now I can do a dual operation, which is, okay, so given a vector field, I give you a function and you give me another function, we can swap the input. What if, given a function, okay, I give you a vector field. So if given I have a function, you give me a vector field, like what I can give you is another function. So what we can define is a map. Okay, I have this correspondence. X, I can map it to xf. Okay, so this is actually a map from vector fields to functions. Okay, and I'm going to give it a name, and this is the f. And it turns out, because of the object it is, and because look here, these one forms are the dual of the vector fields, that actually this df that I'm defining here is a one form. So I have a map that gives me for every function a one form. And now what I can do is to extend it. Okay, and I can just say, okay, so extend it to all the forms. Okay, because here, this thing here, remember, this thing by definition, okay, is just the zero component are functions. Then I have one forms. Okay, well, here I'm now splitting the sections because the bundle is split. Okay, so this is what this thing is. So how do you extend it? So we extend it by linearity. I want things to be linear because I'm working on vector spaces. Okay, this was the whole point of forgetting about the manifold and coming to these bundles. I wanted to satisfy d squared equals 0, and I wanted to satisfy also that it has some compatibility. Actually, it's a derivation of this wedge product I have on differential forms. So I will ask that d of alpha wedge beta has to be, so derivation, I derive the first. Now I will have to put here a coefficient there, okay, for alpha in omega k, say alpha is in omega k, so I will have this property here, okay? So those three conditions, linearity, this thing, and this thing, together with the first definition of the f, they are determining the exterior derivative completely, okay? So this is another basic differential geometric object that we are going to use so much that it was worth it to remember. So exterior derivative, d going from here to here. And just to finish, there is one more operation that we will use. This one is somehow the one I'm not going to motivate so much. It's called the derivative. And for me, the Lie derivative with respect to a vector field, okay? Let's say with respect to x, a vector field, what's going to do is to be an operation, and x is also going to form here. By the way, someone may be thinking that it's a good idea to put here a +1, because this is telling me actually that the exterior differential is increasing the degree of my differential forms. Okay, this happens at any degree. Let me recall, these objects here may be just a function plus a 1 form plus a 2 form. So the differential will be a 1 form plus a 2 form plus a 3 form. So this Lie derivative, I'm just going to define it using the Cartan's formula, which is an operation. Okay, I would say the Lie derivative by definition is going to be just the result of doing insertion and then derivative, or doing plus the opposite, doing first the exterior derivative and then the insertion. Okay, the result, because here we have a -1 and here we have a +1, as you can imagine, so here we will stay just the same. Okay, so this is all the differential geometry we need. I apologize if someone knew this very, very well, probably better than me, but I also wanted to fix the notation. So now we really start. We want to do geometry, okay? And we want to do geometry in this, simplify like this nice way of saying, okay, let's try to deal with vector spaces, okay? So there are geometric structures that are expressed in terms of these bundles. Okay? So now let me recall some of them. So here. So we're going to recall some geometric structures. I'm going to put them. Okay, so geometric structures, the idea is that geometry has been using TM in all the possible ways. What do I mean by that? So this is my TM, and how do I use TM in order to express structures? for instance, what a presymplectic structure is. I'm going to put here. What is a presymplectic structure? So some structures, like the presymplectic ones, are just some of these sections, say omega, which is to form on our manifold, okay? And they satisfy some extra condition. In this case, for a presymplectic structure, is just that the omega equals 0. A dual structure, in the same way that you have said, okay, but that you were doing this for forms, what if you do it for bivectors? Okay, so that's a Poisson structure. So a Poisson structure, I express it also in terms of the tangent bundle, okay, in this second exterior power. So I say, okay, a Poisson structure P is a bivector. Here the integrability condition is a bit more tricky, but not so much. Okay, let me just recall that for any two functions fg, you can define what's called a Poisson bracket. And this has to satisfy the Jacobi identity, okay? If you want like the cyclical thing of F, or bracket F with bracket GH, and you move them and that equals 0. So this is what Poisson structure is, okay? We also have complex structures, okay? So actually these ones are quite interesting because in here you can see how the simplification works, okay? Because I mentioned before as an example of putting a geometric structure on a manifold that you could ask your charts to be complex and your changes of chart to be holomorphic. But that's tough to check and to work with. So what you do is first you translate the complex structure you have on the charts to the tangent space. Because a complex structure at the end of the day is multiplying by I. Multiplying by I geometrically is like turning 90 degrees. So if you know how to turn 90 degrees on a chart, you know how to turn your curves, because vector are equivalence classes of curves, by 90 degrees. So you get this endomorphism, okay, this multiplication by I is actually an endomorphism of Tm. And if I say that I'm multiplying by I, so this is like saying like G squared has to be minus the identity, okay? When I write here endomorphism, this is a bundle map, okay? This means for any element of Tm, okay, an element of Tm is you go to a point of M and then you have a vector there, okay? So you are going to give me another element of Tm, but you are going to keep the point, the base point, okay? So this is like here, this preserves, if you want, the base. I mean, what really is, if someone is a bit bored, I will try to say something smart. What really is a section of the bundle of endomorphisms, because as I said, any operation you can do on a vector space, you'll be able to do on a vector bundle. So for a vector space, you can consider the vector space of endomorphisms. So for a vector bundle, you consider the vector bundle of endomorphisms, and then you take a section. And when you take that section, okay, you make sure that actually you are turning around each point, that you are not doing funny things of bringing vectors from one vector tangent space to a different tangent space. So this is actually the definition of an almost complex structure. We have to ask for an integrability condition, and this integrability condition, it is done in the talking about the plus I eigenbundle. Okay, so this endomorphism is a real endomorphism, and its minimal polynomial x squared plus 1 has complex roots. So I cannot talk about eigenvectors unless I complexify. But if I complexify, I can actually take the eigenvectors, which with eigenvalue plus or minus I. So if you consider the plus I eigenbundle, and this I'm going to call it E, okay, where is this living? So this thing is living in Tm complexified. And I'm going to put the C as here to make it look nicer. Okay, and what I'm going to ask is, must satisfy the following, is involutive. What does it mean to be involutive? It means that whenever I take a section of E and I do the Lie bracket with another section of E, this has to be a section of E, okay? The bracket of sections is gives me another element, but in principle, if I take two sections of E, that in principle would give me a section of TCM. Okay, what involutivity means is that if your structure is to be integrable, has to be involutive. Okay, well, this thing of integrability actually, what's really meaning, and here there is a huge machinery behind, is that you'll be able to find your complex charts. So if you want, people wanted manifolds with complex charts, but to work with charts is very difficult. So what you do is you say, okay, let's say something, instead of the complex charts, give me just the structure on the tangent spaces. And that's just a linear algebraic structure on every point. But that's not enough. Having that won't allow you to have complex charts. So what you do is you put an integrability condition and you say, okay, so now I need this to satisfy an extra condition, and this condition is expressed in terms of the Lie bracket. It's something geometrical, it's not linear algebraic, it doesn't live just at a point. Okay, that condition will allow you to find those complex charts. Okay, but this is a very big theorem, Newlander-Nirenberg. These were complex structures. Let me just add, last class of geometric structures is symplectic structures. Okay, and symplectic, okay, I put pre-symplectic because they are a bit simpler. And symplectic, so is just very similar. The two form, it has to be now non-degenerate, okay, which means that actually when I do the insertion with any vector, that won't be zero, okay? So if you want Ix for, okay, and it has to be also closed, okay? Now, symplectic structures, you like to do mechanics, so okay, phase space, some symplectic manifold, and actually when you go to a submanifold of this phase space, what you lose is that this symplectic form is non-degenerate, so it may be degenerate, so that has a name, it's a pre-symplectic structure. If you start with a symplectic phase space and now you have some symmetries and you quotient out, and at the end you will end up with something with a Poisson structure in there. Okay, so those three are very related and are very related to physics and very useful. Okay, so now the game starts. What is generalized geometry? So generalized geometry is changing the information we are putting at each point. Okay, so we put at each point we put the tangent space, and okay, we took the dual, we took an exterior power, or we took an exterior power of the dual. So now what I want to do is to say, what if at each point, what I do is I consider both the tangent and the cotangent, okay? And I see what that gives me, okay? It's increasing, I increase, if you want, the complexity of my bundle, okay? Of the object I want to use. Yes.
Can you repeat what you said, because you were away like for just 10 seconds. So just repeat whatever you said. Okay,
thank you. Sorry about that. So I was now making the point for generalized geometry. Let me know if I mean if I need to repeat something before. But generalized geometry, what we'll do now is to replace, okay, the information I put at every point which was either the tangent or its dual, either an exterior power of the tangent, an exterior power of its dual. Now we'll mix this, okay? We'll make my, if you want, my starting point more complex, okay? More involved. And why? Why do we do that? Okay, let's play around first. What happens if we had to start to do geometry with this tangent plus cotangent? Let's see what can we do now with this. So let me just, the best thing is just to show you with examples. Let's start with a presymplectic structure. A presymplectic structure, it's a bivector. That means that it can be seen also as a map that if it's a bivector, if you give me it's a two-form. A presymplectic structure is a two-form. So if it's a two-form, you give me a vector, okay, an element of Tm, and I can give you an element of T star m. So now, actually, all the information I have there can be expressed as the graph of this map. The graph of this map, which by definition is just x plus, and here you could use this, okay, you can put this. Sometimes this operates, just because for the side is, I will just put this so that it looks more like a graph. This for x in Tm, okay, this is a subbundle of this. Okay, two observations. The first one is that what I'm really considering is this, but I'm not writing it to make it lighter, okay? But it is a direct sum. At every point, I'm considering the direct sum of the tangent and its dual. Second observation is that I'm using for x, y, all this notation I put, both for sections and both for elements, okay? So here you see I'm just saying x in Tm because what I'm doing here is just linear algebraic. I don't need to consider a smooth section. I am just taking the elements and defining these subspaces at each point. The thing is that actually they give me a mu bundle, and this is a sub object, okay? It's a sub bundle, okay? So a sub bundle, as you can imagine, if a bundle, vector sub bundle, if a vector bundle was like having vector spaces at each point and with nice properties, so a subbundle will be okay. In here, I will have at each point subspaces of the original vector spaces, and in such a way that I have these trivializations. Okay, these like locally looks like a product, and the changes of chart of trivialization are actually linear. Okay, so this same game I did here now, I can do it for also for Poisson structures because they are just a dual. Okay, it was just hard to express the integrability condition, but what I'm doing here is just deducing some object related to Tm plus T star m. So now a bivector takes a one form and gives me a vector field. So the graph of this, okay, expressed in the same way, is the same, a bivector, a subbundle, okay, here. Good. Can I do this for complex structures? Okay, this is a bit, I will have to force it a bit because complex structures, they fit very nicely in with the tangent bundle. They're just endomorphisms of a tangent bundle. So, but if I insist, and I do this for a good reason, I could do the following. I could say, okay, you want something on Tm plus T star m? Don't worry, because if you know how to go from Tm to Tm, you can dualize this map, and you will go for from T star to T star. So you will be able to set up. Here we change the sign just for convenience. This map, which is in block notation, okay? These are blocks Tm and T star m. And I will give it the notation of just curly J. So this curly J is actually an endomorphism of Tm plus T star m. And well, I was actually fast enough to put a minus there so that I get also this property. So that it looks quite complex, like a complex structure on this Tn plus T star. And with symplectic structures, and now there is a key property, non-degenerate. Okay, if I'm playing this game that I can put endomorphisms of Tn plus T star n, I can do the following. I can use the off-diagonal entries of those endomorphisms and say, okay, look, if a symplectic form, as a form, it takes some vector and gives me a one form, I can plug it in here, omega. And here I can put omega minus 1, and of course, if I want this to square to minus identity, I will have to put a minus there. And this also gives you some map, okay, whose square is minus identity, and it's an endomorphism of Tn plus T star n, okay? So this, so far, it's a bit like not very impressive. Why? Because, okay, I have set up a new bundle. I mean, it's true I've got smooth objects related to Tn plus T star n, but they are not dependent on, for instance, like not every vector subbundle of Tn plus T star m is very, I mean, it's something very general to have a vector subbundle of Tn plus T star m. Okay, so what we do is we are going to upgrade our Tn plus T star n, which is sometimes called this generalized vector bundle. How do we upgrade this? We realize that we didn't, at every point, we didn't just add some information to some, like I have some information here, which is the tangent, and then I have here some other different thing that has nothing to do, and I put it together. No, we were putting a tangent, a vector space at each point, and it's dual, okay? So there is a duality between the two of them. This means that actually, if now I consider two elements of Tn plus T star m, okay? So I consider x plus alpha and y plus beta, I'm able to do a pairing, okay? I'm able to give a number for those. I just have to do, okay, since they are dual, so I can take alpha of y plus beta of x, okay? So now let me discuss here on one side, what is this pairing like? Okay, okay. Okay, so now what about this pairing? So let me recall it. Remember, we denote vectors by x and y, we denote forms by alpha and beta, and I have this thing. Okay, when I put this sign, so the first we think about, or if we show this to a child, so he may think about the inner product, okay, but not something. This is a bit of a strange inner product, because if I take two vectors and I take the product, or I take two forms, this is 0, okay? So this is not a non-degenerate pairing, okay? Actually, I have what's called, okay? So Tn and T star m are isotropic, okay? What does it mean to be isotropic? So this is just for a vector space with some bilinear pairing, okay? So I say that a subspace, okay, this is like V with, okay, a vector space with a bilinear form. Okay, don't say inner product, because inner product somehow, let me say just symmetric. Even though, I mean, actually, no, I just need bilinear form. So to say what is isotropic. So I have that a subspace of this in here is isotropic if what happens is that for any two vectors that I take in that subspace, the product is 0. Okay, I can see now there was a blackout, perhaps there was also a bit of disconnection now. Can you nod if that's the case? Or I can't hear you now. You can either do this like was there a disconnection? Ah, it's okay for now. Okay, because perfect. So this is an isotropic subspace. So it happens when I have these pairings, okay, that are not necessarily positive definite. And there is something good about the isotropy, that when the characteristic of my field, okay, if the characteristic of the field, okay, a vector space over a field, of course, in our mind, and in this course, it's just real and complex. I'm going to state this in general for our joy, but if the characteristic of the field is different than 2, then you have that a subspace is isotropic if and only if. And now I just say U with U is 0 for all U in W. Here, by the way, there was a mistake. Yeah, that was W. Okay. So let me just, since this is a course, I think we have to do some proofs. So I'm choosing the ones that are either very simple will help us, or the ones that are very relevant. So, well, of course, this direction, if it's isotropic, that condition is much weaker than the one I had before. So there is no doubt that this is done. The only difficult direction, and the surprising one, if you want, is the other one. How come it is enough to do just one vector with itself? But since this happens for every vector, we can do what's called the polarization trick, which is given two vectors of your subspace, you know that all the pairings of a vector with itself are 0, okay? But now by bilinearity, so we have U plus, okay, here actually, yeah, I'm going to say symmetric. Huh. So that this, I don't have to start saying, so because now I want to write this, okay, I want to write this. And now see what happens, 0 equals this sum, but the property I have is actually that this is 0 and this is 0. And since I was careful to say that a characteristic of the field is not 2, that means that 2 is not 0. So that means that UB has to be 0, okay? So like the inner product UB has to be 0 for any arbitrary UV in W. So that means that I'm done as well, okay? So this is this new space isotropic that are appearing in our metric, because we are not going to study just arbitrary pairings. In our pairing point-wise, look at what's happening. So point-wise, the pairing we have is actually like this. You can find a basis, okay, such that the matrix corresponding to this pairing is 0, 1, 1, 0. Okay, by this, what you have to do is at every point you choose a dual basis of TPM and T star PM. If you choose a dual basis so that this is 1, then of course, since TM and T star M are isotropic, you get this. Okay, so this is actually a pairing of signature and N, because you can transform, you could transform this matrix on something which is like this, okay? And remember, this is the signature. The pairings, I just count the positives and the negatives here. Of course, I'm taking N is the dimension of the manifold, okay? And there is a fact that it's quite intuitive, but I'm not going to say the proof is, what is the maximal dimension of an isotropic space, okay? So the maximal dimension of an isotropic space is actually n. Okay, if you want to think about it, also think like if you had something bigger in this matrix of the matrix of the metric, you would be of the pairing, you would be able to put a very big zero block, and that won't be nice. Okay, so but let's leave it like this Tm and T star m are actually maximally isotropic. Okay, having said this about this new pairing, which is different, quite different to the usual inner product, let's come back to the okay, this sometimes lower than I would like. Okay, here it goes. Okay, so let's now consider that I have this Tm plus T star m upgraded to this bundle with a pairing. And what happens is that the objects I had defined before, this reinterpretation of geometric structures, it's compatible with this pairing in the sense that these vector subbundles that I have here are actually isotropic. And the isotropy comes actually from the fact that it is a skew form, okay, that these are skew. So that property is captured by this pairing. Okay? If just you want to think about it, you can just take the, remember isotropic would mean that x plus omega x plus omega x has to be 0. But okay, what is this? So this is just omega xx. Okay, so it is 0. Okay, let me put the 0 on the other side. It logically. Okay, this thing, any vector with itself is 0. So this is isotropic. But it also has the right dimension because this was, here I have Tm. So this is actually maximally isotropic. Okay. And on the other side, these operators, these endomorphisms J, they satisfy that they are skew symmetric for this pairing. Okay, for skew symmetry, what I mean is you want this identity that if you have this is 0. Here, by the way, when I have sections that are not necessarily vector fields, I'm using this notation usually, okay, for sections of Tn plus T star n. Okay, so there are skew symmetric endomorphisms. Okay, so this starts to be nicer because I'm somehow getting some properties. Okay, here I'm also making use of this skewness here. The thing is that still I haven't reached the integrability of these structures, and this will be done by upgrading once more my generalized vector bundle. And my generalized vector bundle, I can upgrade it by considering a bracket. Now, a bracket, we are used to the bracket of vector fields. You give me 2 vector fields, I return you a vector field. Now I need a bracket on this generalized tangent bundle. So you have to give me 2 generalized vector fields, and generalized vector fields are a vector field and a 1 form. And I have to return you a vector field and a 1 form. Okay. So the vector field, if you give me all those things, almost the only possibility you have is the Lie bracket of those vector fields. Okay, and now for the 1 form, we had many operations around. Okay, so I'm just going to give you the one that will work for us, which is the following. You take the Lie derivative with respect to x of beta, and now you take the insertion of y in the alpha. Okay, let's look at this now with a bit more detail to see how does it work exactly. Okay, so there we see it. I'm going to write it again in case someone is taking notes. This has a name, by the way. This is called the Dorfman bracket. So I recall what it is: x plus alpha, y plus beta. It gives me xy plus lx beta minus iy d alpha. Okay, brackets. Bracket usually refers to something that's q-symmetric. Okay, but look at what happens when I do the bracket of a section with itself. Okay, so if I say x plus alpha bracket with x plus alpha, okay, this is the bracket of x and x plus lx alpha minus ix d alpha. Okay, look, x, this is 0 because the Lie bracket is q-symmetric, this we know. Lx is an operation I've defined before. So, and that operation was defined in terms of, it was d of ix alpha plus ix d alpha. That's the derivative, and I'm subtracting ix d alpha. Oh, there are two terms here vanishing, but it is not 0. What I get is this. I get d of ix alpha. But ix alpha, okay, which is just, if you want, of alpha x, d of alpha x, is actually d of the pairing of these two sections. So this is actually telling you that this bracket in general is not skew. But when you take sections of an isotropic bundle, it will be skewed. This is a price we have to pay, okay? This not skew symmetric is a price we have to pay to have some nice properties. Okay, so nice properties, which is something you like can be proved, is that whenever you give me some sections of Tm plus T star m, it still satisfies some nice properties which are a kind of Jacobi identity. But here you have to be very careful because it's not skew symmetric. So you need to write the Jacobi identity in this way, because you won't be able to recover the cyclical Jacobi identity. Okay, it's Jacobi but not cyclic. And also it talks very well to the pairing. Okay, what does it mean? That if you give me the pairing of two sections, now with the other section I want to act. How do I act on this is a function now? How do I act on a function if U is a vector and a one form? So just forget about the form and I project to Tm and I use this to derive the pairing. Okay, so this, it acts as a derivation in the sense that now actually here I can take the bracket, okay, and those here are all Dorfman brackets plus V U. Okay, so it's actually this derivation of the pairing. Okay, so now with this bracket we come back here and we are just upgrading further, okay, another layer of a structure on this generalized tangent bundle, okay, and this structure is the pairing. So with this structure, what happens is that this graph and this graph, okay, because the two form is closed and because here you satisfy the Jacobi identity, those are going to be involutive. Okay, in this sense I put here, but for the Dorfman bracket. And actually it works really well because for any two form you have, if you give me a two form, I will always be able to take its graph and have something maximally isotropic. So it turns out that that two form is closed if and only if the graph is involutive for this bracket, okay? And the same for the Poisson bivector. On the other side, on the side of this complex and symplectic, where I wrote this endomorphism, what I have is plus, the condition is that the plus eigenbundle, but the eigenbundle of the big J, of course, because, okay, this is my structure now. So this is just some L living in Tm plus T star M complexified. This has to be involutive, okay? Again, now, okay, I'll say it for last time, for very last time, with respect to the Dorfman bracket, okay? So now there are some structures that before were different, and now somehow we see they are satisfying the same properties. So Pre-Symplectic and Poisson, which were kind of dual, now I can describe them as subbundles of this Tm plus T star M that are maximally isotropic and they are involutive. This has a name. These are real, but they are Dirac structures. These are Dirac structures, okay, as they were introduced by Courant and Weinstein. And what I have on the other side, this way of looking at complex and symplectic structures in a unified way, okay, is what's called a generalized complex structure, as introduced by Hitchin and then developed by Gualtieri, Cavalcanti, and others. So the first ones are from the end of the 80s, and the generalized complex structures are from the beginning of the noughties. So this extra structure we've put on Tm plus T star M is actually a general structure that a bundle can have, okay? And this is what's called a Courant algebra. So what I'm going to do is to say that definition, and what we'll do later is just to stop at some of these structures. So just, I'm going to say here, definition, okay, well, this is kind of a definition, it's not, okay, let's say that Tm plus T star M together with the pairing, together with the bracket, and together with the projection to Tm, okay, and now I'm going to denote it just by pi, and this is why I was keeping this letter, okay, is a Courant algebroid, as introduced by Liu, Weinstein, and Chu. So it will be a vector bundle with some non-degenerate pairing and some bilinear operation on sections, which is not skew, but satisfies the properties I had before, okay? So the properties I had before is that actually when I take the bracket of by one section, this is a derivation of both the bracket and this in here, and the other property that I had before was what happens when you take this. So if you, okay, these are like this is the if you want the core of a Courant algebra, okay? So this object that we have here is replacing our usual tangent bundle that we use to define structures. So I would like to mention what are symmetries of this Tm plus T star M, because this is the game I'm trying to play here is that I'm replacing Tm by something more complex, but I'm going to replace the whole thing. So now actually I'm even going to change the diffeomorphisms of my in my mind. Now they won't be just diffeomorphisms of my manifold. They are going to be called these generalized diffeomorphisms. Okay, these generalized diffeomorphisms are going to be the symmetries of Tm plus T star m. So are just maps of Tm plus T star m on Tm plus T star m, and they're going to be, of course, smooth. And the idea is that they cover some other diffeomorphism here on the base manifold, and you just have to ask those maps to preserve the structure. Okay, so what does it mean to preserve the structure? It means that, okay, what happens if I take the pairing of two images of two generalized vector fields? Okay, so this is going to be here just by changing the base point, but essentially it's the same as taking. Okay, so they preserve the pairing, and as you can imagine, so they will satisfy the same properties for the bracket and also actually the projection to M. Okay, so 1 pi, and if I do first F and then the pi, the corresponding pi there, so this will be the same as this in here. Okay, so this is the definition of a generalized, okay, pairs. So examples of this, okay, of such maps that they preserve all these things. So whenever you have a usual diffeomorphism, you can always consider this in here. You take the push forward and then you take the pullback by the inverse on the forms, zeros here. So this, okay, if I call this is a group which is the generalized diffeomorphisms of my manifold. So this will be an element of the generalized diffeomorphisms of my manifold. Okay, but there are more than that, and this is the idea of the generalized diffeomorphisms. And the other ones are that for B a closed to form, it turns out that this map, I put here the identity, which I denote by 1. Okay, here I'm still using these block matrices. If I do this, what it means is, okay, that if I have x alpha, I do x plus alpha plus now the B is acting on the x, which is there, okay, in the block matrix notation. So I do ix b, okay, and that gives me a 1 form because it was B is a 2 form, okay. So this element is also gdiff of M, and there is something you can prove, okay, putting this as facts, is that the generalized diffeomorphisms of the manifold are exactly the semi-direct product of those diffeomorphisms and those two forms. That means that I have more structure, okay, I have more transformations preserving this current algebraic structure, but they are just these two forms, okay? This, by the way, is what is called B fields, okay? And those are part of the reason why generalized geometry is helpful sometimes in physics. So in order to finish, let me start to do what are our objectives, which is, okay, I'm going to talk about Dirac structures, then I will talk about generalized complex structures, and then we will finish talking about this thing of complex Dirac structures, which is something new. Okay, so here what I did is just I gave you some names, but I didn't even define what a Dirac structure is. Okay, I just told you, okay, it is related to this series of Dirac structures. I just put Pre-Symplectic and Poisson structures on the same under the same framework. So Dirac structures. So definition. So now what I do is, before using Tm and T star M, I could take Pre-Symplectic and Poisson and see that they give me the same kind of object. Which kind of object? So they gave me a maximally isotropic, which if you want, you can also call Lagrangian if someone is used to the notation, subbundle, okay, L of Tm plus T star M, which is involutive, okay? That is moreover, okay, involutive. So that means that the sections of L will give you a section of L. So this was a kind of object I found when I was looking at Pre-Symplectic and Poisson through the generalized glasses. So these are the Dirac structure. Okay, examples. Well, Pre-Symplectic and Poisson. I mean, this is the whole point. Was these are the thing. Okay, if I don't give you more examples, so this will be a bit meaningless. So just other examples that I can put is to take a subbundle, which is, and I have to ask for it to be involutive with respect to the Lie bracket. The bracket. Okay, so now I can consider the annihilator of this subbundle. What is this? Is another subbundle, but of forms. Okay, the annihilator of a vector space will be the forms. So here I'm going just to, for convenience, to say describe it at each point. Okay, for some p, such that alpha of p is equal to 0. Here, what I'm stressing is, okay, for some, I'm stressing that is just a linear algebraic object. Okay, so you can define L to be E plus, and here again it's a direct sum, okay, but I'm just putting just a normal sum. This, if you think about it, I have E and an annihilator of E. So whenever I take the bracket, look, this is inside Tm. This is inside T star M. So, sorry, whenever I take the pairing, okay, not the bracket, whenever I take the pairing, if the two elements are in E, I'm done. If the two elements are in annihilator of E, I'm done. Why? Because Tm and T star M are isotropic. The pairing of any two elements there is 0. But if I take a pairing of an element on E with an element of annihilator of E, I was careful enough to put annihilator of E so that this will be also 0. So this is isotropic, okay? So this is isotropic, and then because I have here E as a bundle, and the annihilator of E has as rank, as the dimension of the fibers, the total dimension minus the dimension of the subspace, okay? This is how annihilator, the dimension of the annihilator of a usual vector space is. So I have that the dimension of E plus annihilator of E is actually the dimension of the manifold. So this means that this is maximally isotropic. So it is maximally isotropic, okay? And because I chose this to be involutive, is also involutive. So it is a Dirac structure, okay? So this would be an example which is neither pre-symplectic nor Poisson, okay? So now the question I'm going to leave, I will answer tomorrow, and here I can see I still have some lines. Okay, so the question I will want to answer tomorrow is, what are, to start with, the maximally isotropic, I would like to know some abundance, but let's start by doing linear algebra, okay? So this is a linear algebra question that, yeah. So with on a vector space plus its dual, this is okay, the linear algebra model of Tm plus T star m. What are the maximally isotropic subspaces? Because this is the first step to know better what these Dirac structures are, and later we'll have to deal with complex Dirac structures, okay? So first we have to do it on linear algebra. You know the pairing, okay? You know the and here what's that you have here, your vector space V plus V dual. So let me just, I'm going, in case anyone wants to try today before tomorrow. So let's let me say how I will start. So you take something which is maximally isotropic, and the idea is to consider the projection to V of this thing here, okay? Because, look, one example we had was pre-symplectic structures that were graphs of a symplectic form, pre-symplectic form, that were taking vectors to one forms, okay? So what I'm asking now is to say, okay, what can you do if you try to see any Dirac structure as a graph? But as a graph, as we see here, it's not a graph, because for every element on here I have the whole annihilator, but still perhaps it's a graph where for each vector I tell you all the possible one forms, okay? So for x in E, the first question would be, what are the possible alpha such that, okay, alpha in here, okay, it's, bear in mind, I'm being consistent with the notation, I'm just changing a bit the space going from bundles to vector spaces, but this is still a one form. What are the possible alphas such that x plus alpha belongs to L, okay? So if you try to give an answer to this question, you may end up with a nice description of what are the two ingredients that I need to describe maximally isotropic subspaces. One of them is this one, and the other one, you may find it today. If not, tomorrow, I will tell you when we start. And this is all I wanted to say in this first session, and I leave you with this open question. Thank you for your attention. I cannot hear you. In case.
Now you hear me, right?
Yes, now I can hear you, yes.
Okay. Okay. Well, thank you very much, Roberto. I was asking if there are questions. They are shy. So maybe I have like a question like, well, just historically, like, where does this Dorfman bracket appear? Like, is this, I mean, was this studied before? Because I mean,
the thing, it was at the end of the 80s. Actually, if someone has looked at the subject before, some of the people call it the current bracket, okay, because it appears on current algebroids. And but if the thing is, the Dorfman bracket is not skew-symmetric, okay, and the current bracket, when it was introduced, since they wanted to have a bracket, so they took the skew symmetrization of this bracket, which you can always do. Okay, you just force it to be skew symmetric. All the other properties, they just spoil them. You have to add terms for them to be satisfied. So at the end of the 80s, there was this work by Dorfman where she was working on some other things, the Poisson, blah, blah, and then there was this operation there, okay, the skew symmetric one. And that was published, I think, year 87. And then, okay, in parallel, Curran, who was a student of Weinstein, was working developing these Dirac structures, okay? And there they had, okay, this bracket, this Curran bracket, which was a skew symmetric part. So somehow, they were looking at very similar problems, okay? The Dorfman bracket, I think the Dorfman bracket, I wouldn't say at that point it was used, but actually I don't know, okay? It's just a guess, but somehow because the theory of Dirac structures was developed in a very sound way, okay? And it continued, so that led to current algebroids, and it made sense that the bracket of a current algebroid was a current bracket, but this was still the skew symmetric part. With the time, people realized, including myself, but not everyone agrees. For instance, Hitchin prefers the skew symmetric bracket, that the non-skew symmetric bracket is actually more convenient when you want to do operations because of its properties, okay? So we started, even though, for instance, my thesis uses the skew symmetric, then I write things with the non-skew symmetric, with the Dorfman bracket. And then when I realized, or some people realize, okay, this bracket appeared before and it's due to Dorfman, so we should give her credit. So when this on purpose, I use Dorfman bracket and current algebra because here, okay, everyone has its share of the story. Some people may refer to it also as the current Dorfman bracket. For me, it's a bit too long, okay? And also, okay, current, it was skew symmetric, so I'm actually working with a non-skew symmetric one, which is the one I can see in a paper of Dorfman, even though it's just an equation there, and I mean, you really have to look for it. It's not on your face. If you open the paper, it takes you some time to put things together. Okay. I hope this answers your question.
Okay, thank you very much, Roberto. Are there other questions? If not, well, there's one question here. I'll hurry up to the other end of the room.
I have just one question out of curiosity. And as I understood, current algebroid is not a Lie algebroid because the space of sections is not a Lie algebra, right? It
yes.
doesn't satisfy the Jacobi identity. Is there any notion of something like a current groupoid integrating the current algebroid or something like that?
Yeah, well, these things are, they are. It's a question there. I don't know what the status is. Right now, I think there are several approaches to that. I'm not an expert, but okay, it's a problem that has been dealt with. But I can't tell you out my mind like, okay, is the object? These are, for me, they are they end up being quite complicated. Some people use this graded geometry to give answers to these questions, and and it sometimes also depends on the approach you take. So As far as I know, there have been some approaches. None of them is, say, simple enough to have grabbed my attention to say, okay, well, this is something we should definitely use. Okay, for me, it's still an answer that is given to this question, like just for the sake of an answer to that, but it doesn't develop further, as far as I know.
Okay, thank you very much.
Thanks. Some other questions? So if not, let's thank Roberto again. And well, we'll resume at 11, right?